Start, sir. You can start, sir.
Good afternoon and welcome to the first live session of the course. So today we'll discuss some aspects which we thought that we should review based on your discussion on the forum. And also, I'll quickly update you on the requirements for obtaining certificates, as well as about writing the exams. These informations are already available on the website, so please go through the website. But anyway, on this first live session of the course, I'll just take one slide to just go through that for your quick and ready reference. So, is the screen, can you see the screen? Disha, you are online. Can you please say whether you can see the screen?
It's visible, sir.
Okay, fine.
Please make it full screen, sir.
Okay. So now, so we have decided to, this will be the today's topic. I'll briefly tell you about the evaluation and certificate policy associated with the course. Then we'll take a simple temperature control system as an example. And in that connections, I'll tell you about the role of various transducers, and then come to a brief discussion on pressure to current converter as well as current to pressure converter that are frequently required in a control systems. And then based on your inputs in the forum, I'll also talk about U-tube manometer. So we'll review some of the aspects of the U-tube manometer that we have already discussed during the course. So let me start with your evaluation and certificate policy. You have to write an exam. For that, you need to visit center as of now. So the date of the exam is 25th April 2021. There will be exams in 2 sessions. The morning session will run from 9 to 12, and the afternoon session will run from 2 p.m. to 5 p.m. Now, the evaluation policy is as follows. Your final score has 2 components. One component comes from your scores in assignments, and another component is coming from your final exam. Now, if we consider that the total score is 100, then 25% contribution to the final score will come from the assignment, and 75% weightage is for exam score. So the maximum assignment score may be 25, and the maximum exam score is 70. That's the weightage. Okay. So for the computation of the assignment score, what will be done is your 8 best assignments will be considered. Note that you are supposed to submit 12 assignments, but all 12 assignments will not be considered. Only the best 8 assignments will be considered. And 25% of the average of the 8 best assignments will be considered for average assignment score that goes to a final score. And 75% of the final exam score out of 100 will go to the computation of the final score. So that's how your final score will be computed. And there is eligibility criteria for certificate. So there are restrictions on the scores on both average assignment score as well as exam score. To be eligible for a certificate, you must get 10 or more out of 25 for the average assignment score. Similarly, you must get 30 or more out of 75 in the exam score. Note that both the conditions must be met. Although the minimum score is 40, 10 plus 30 is 40 out of 100, but this will come both from the average assignment score as well as exam score, subject to those minimum conditions, that minimum 10 marks out of 25 from the assignment score and 30 out of 75, minimum 30 out of 75 from the exam score. So I strongly suggest that you submit all the assignments regularly within the due time. So now let's go through a simple control problem. What you see is a heat exchanger. So a cold process stream is going through the exchanger, and that is being heated up by another hot process stream. All I want is to heat up this cold process stream at a given temperature. That means the cold process stream that comes out at this point of the heat exchanger, at the outlet of the heat exchanger, must have the desired set temperature. And we plan to do that by controlling the flow rate of this hot process stream. So that's the control problem. So it's a simple problem, and we'll see how a feedback control loop will look like for this simple control system. So the first thing that is required is the ability to know the temperature at the outlet, right? So you need a temperature measuring instrument to measure the temperature of your control variable. Here the control variable is the temperature of the cold process stream. So let us look at the block diagram first that you are familiar with. So the process sits here in this block. So this process is nothing but the heat exchanger that we have seen in the previous slide. So this is the temperature of the outlet stream that is coming from the heat exchanger, which needs to be maintained at a desired set point. So the temperature of this control variable is measured by a measuring element, which may be a thermocouple here, let us say. Now, this information about the measured temperature goes to a controller mechanism. The controller mechanism may consist of a comparator as well as a controller. So the comparator is the part which will compare this measured temperature with the set temperature. And their difference will be considered an error signal. Note that when error signal is 0, it means that the set point temperature and the measured temperature are same. But when the error signal is not 0, it means either the measured temperature is higher than the set point or lower than the set point. So that error signal goes to the controller, and then the controller decides what needs to be done. That means if the temperature of the cold process steam, which is my control variable, is below the desired temperature, the controller would increase the flow rate of the hot process stream to attain that temperature. Otherwise, it will lower down, as the case may be. So depending on whatever is required, the controller will decide what should be the flow rate of the hot process stream. So that information from the controller will go to the final control element, which will execute this decision. That means which will change the flow rate of the hot process stream. So that instruction goes to the process. And here there is load variable. That means there are disturbances to the process which will try to change this change the condition of the control variable, and the controller actions will be required. So now this is a feedback control loop. So this explains the way a feedback control system will work. Now, in this particular course, we are talking about mainly this part of the control system, which is measuring element. Note that when you are looking for a measuring element or a sensor for a control system, that particular measuring element must receive input and give output that is suitable for the purpose of the control. For example, in this particular example, it is not convenient to use a marker in glass thermometer as measuring element, because the output of the marker in glass thermometer, which is basically the displacement of the marker in the capillary, cannot be transferred to this comparator so easily. So in principle, we can adopt certain mechanism by which that can be done, but it's not so convenient. Whereas, let us say a thermocouple, which will give me a millivolt as output, which is an electrical signal, can be very easily conveyed to this comparator unit or to the controller unit. So let us now look at a very simple schematic of the units that will be required for this particular control system, which is a simple temperature control system. So this is the process we are interested in, maintaining the temperature of the cold process steam at a desired level. So first, we want to measure the temperature of the cold process steam, the control variable. So we measure using a thermocouple. So the thermocouple output goes to a transducer, which gives me an output in the range of 4 to 20 milliampere current. So the output of the thermocouple is basically converted to an electrical signal, to a current signal in the range of 4 to 20 milliampere. Note that this 240 voltage that goes as input to this transducer is basically the power requirement for this electrical unit. Now the current signal in the range of 4 to 20 milliampere is basically a linear function of this temperature. We can consider, say, 4 as the lower range of this temperature, at 20 milliampere as the upper range of the temperature, and anything in between will be linearly interpolated. So 4 to 20 milliampere current signal goes to the controller. If I'm talking about a digital control system, most likely the controller is a computer. So this computer also needs an auxiliary and a power source, say 240 volt. So in this controller, you can put the set point. You can specify the set point in the controller. Like you have seen in the previous slide, remember the role of comparator. Now, in this computer, you can actually write a program for, say, proportional controller. So then the gain will be as an input, or proportional integral control, proportional integral derivative control. All these things can be written. So depending on the algorithm that you write or the algorithm that you use, it will have different inputs for the controller as well. Those gains of the controller, right? You know that those are typical symbols, K, tau I, tau D, etc. So the 4 to 20 milliampere current signal corresponding to the measured temperature goes to the controller, which is the computer, and then the controller or this computer decides what should be the flow rate of this hot process stream through the heat exchanger. Now, that information again is sent by the computer as a 4 to 20 milliampere current signal. Now, we are controlling, or we are manipulating, we are changing the flow rate of the hot process steam using a pneumatic control valve. Now, this pneumatic control valve does not understand electrical signal, current signal. It only understands a pressure signal in the range of 3 to 15 psig. So, you need a converter which will convert this 4 to 20 milliampere current signal to 3 to 15 psig. Note that the current signal, which is in the range of 4 to 20 milliampere, will be converted to a pressure signal in the range of 3 to 15 psig. Information content must not be changed. So the same instruction that was sent by the controller or computer as a current signal in the range of 4 to 20 milliampere must be intact in the pressure signal in the range of 3 to 15 psig. This is done by this converter. So what kind of conversion this converter is doing? It is converting a current signal to a pressure signal. We call this I to P converter. Note that this converter also needs the power source, say 240 volt. In India, we have 240 volt. There are countries who work on 120 volt. And also the 20 psig air pressure. So that is also required for this converter. Now, the 3 to 15 psig pressure signal goes to this pneumatic control valve. So the valve top receives this pressure and it decides the opening through the control valve. So based on that, the flow rate through this heat exchanger will be controlled, and thus the temperature of this cold process steam will be maintained. Note that this current signal 4 to 20 milliampere basically means, you can interpret it this way, when the minimum range of output corresponds to 4 milliampere current. So when there is 4 milliampere current is output from the transducer, you are basically saying that there is no input to the transducer. And when 20 milliampere current is the output from the transducer, then input is at its maximum level. Now, frequently, input at minimum level is 0. But we do not say 0 milliampere current as output signal corresponding to 0 input signal. Such non-zero output from the transducer for the minimum level of input helps us to differentiate between a faulty output or an actual output from the transducer corresponding to 0 input. So this is helpful in that sense. So now, in this example, we saw that 4 to 20 milliampere current is being converted to 3 to 15 psig pressure signal. So an I to P converter, or current to pressure signal converter, is required here. Similarly, there will be occasions where a pressure signal needs to be converted to the current signal. So P to I converter converts pressure to current, and I to P converter converts current to pressure. So now let's quickly take a look at how I obtain an I to P converter or P to I converter with help of the transducers that you are already familiar with. You are familiar with flapper nozzle system. You are also familiar with LVDT, or linear variable differential transformer. Now, if I quickly recap, a flapper nozzle system consists of a fixed restriction and a variable restriction. So air supply, typically in the range of 20 psig, is supplied at this end, And depending on the gap between the nozzle tip and the flapper, a back pressure will be developed. Note that as you bring this flapper closer and closer to the nozzle, this pressure increases. As you take it far away, this decreases. So this output pressure is basically a function of the distance of the flapper from the nozzle. So this pressure can be calibrated with respect to this flapper nozzle distance. Now, if you look at the relationship between this output pressure and the flapper nozzle gap, note that when this flapper comes very, very close to this nozzle, and in the limiting case, when there is no gap between these two, you will get this back pressure same as the supply pressure. And then it will fall as you take it further away. So if you look at how this output pressure vary with change in this gap between the flapper and the nozzle, you get this typical curve. And if you look at the curve, the output pressure in the range of 3 to 15 psi, this varies linearly, almost linearly. So this flapper nozzle system is basically a pneumatic transducer which converts this displacement signal to this pressure signal. Similarly, this linear variable differential transformer is an electromechanical transducer. So this electromechanical transducer converts the displacement signal to an electrical signal. It essentially consists of one primary coil and two secondary coils. These two secondary coils are connected in series opposition. And this soft iron core provides the magnetic coupling between these two coils. Now this ferromagnetic core is physically connected to the object whose displacement is to be measured. Now, as that object moves, this soft iron core also moves. So different part of it is exposed differently to these coils. Accordingly, a voltage is induced in the circuit and there will be a current flow. So if you look at this figure, it will be clear. So this is the core. Let us say this is the soft iron core. Typically it is say nickel iron alloy or ferrite. And this is the primary coil. And these are two secondary coils connected in series opposition. The primary coil is excited by a sinusoidal voltage of amplitude 1 volt to 15 volt and frequency 50 hertz to 20 kilohertz. Now in this particular picture, you see that the core is centrally located. And in this case, both the coils, both the secondary coils, actually both the secondary coils are identical. Both the secondary coils are equally affected. But so the voltage is induced in this secondary coil as well as this secondary coil. But since they're connected in series opposition, the net voltage is 0. net output voltage is 0. So there won't be any current flowing in the circuit. But in this case, where this core is pushed up, you now see that this secondary coil is affected, but this secondary coil is not. So a non-zero voltage, a non-zero output voltage can be obtained from the circuit, or a current will be flowing in the circuit. And that current will be proportional, or the output voltage will be proportional to the displacement of this core. So this is how the linear variable differential transformer works. So now let us see how we can obtain a pressure to current converter with help of this flapper nozzle system and LVDT. So look at this part. This part is nothing but the flapper nozzle system that we have discussed. And we have seen that this output pressure is the result of this gap between this flapper and nozzle. And this is into depending on this gap between flapper and nozzle system, so you'll obtain a back pressure. We have seen in the previous slides. We have also seen that the output pressure is typically linear. The relationship between the gap and this output pressure is linear in the range of 3 to 15 psi. Now, this pressure, this output pressure, is received by these bellows. So the bellow will expand. Now this bellow is connected to this core. So this pressure goes inside the bellows. So bellow expands. So core also moves up. The reverse thing happens if the pressure goes down. So this pressure basically converted to the output current of the LVDT. So this pressure signal is getting converted to this output current. So this will work as PI converter. So this pressure is being received by the bellows. So bellows will expand. Since bellow is connected to the core, so there will be movement of the core depending on the variation of this pressure. And we have seen as the core moves away from its centrally located position, these two coils will no longer be identically induced. So there will be a non-zero output voltage or output current, which is proportional to this pressure signal. So this is how we will have PI converter. Now, for I to P converter, we can have this kind of mechanism. So this is the principles of current to pressure converter. Again, this is the flapper nozzle system, except this, we have a flapper nozzle system. This flapper is, let us say, spring loaded here, spring restrained here. And the 420 milliampere current that I have to convert it to the pressure signal is being sent here. So as I send this 420 milliampere current, I produce a magnetic field here. So this magnetic field pulls down this flapper, and that's how it maintains the gap between the flapper and the nozzle. So higher the strength of the magnetic field, more the flapper will be pulled towards the nozzle. Less the strength of the magnetic field, the gap between the flapper and nozzle will be more. So by varying the current in the range of 4 to 20 milliampere current, you can vary the magnetic field, and you can thereby maintain a gap between, variable gap between the flapper and the nozzle. Accordingly, this signal will be obtained. So 3 to 15 psi signal pressure can be obtained corresponding to 4 to 20 milliampere current by this. So this is I to P converter. So now we'll quickly talk about a second order instruments, particularly the step response of the second order instruments. We'll just review that quickly, as some of you have asked for it on the forum. Now, you know that a first order system can be mathematically represented by a first order differential equation, by a first order ordinary differential equation with constant coefficients. Similarly, a second order instrument can be mathematically represented by a second order ordinary differential equation with constant coefficients. In general, we can say an nth order instrument or nth order system can be mathematically represented by nth order differential equation with constant coefficients. Now these differential equations, if you look at these differential equations, this represents an nth order differential equation with constant coefficients. Now, the dependent variables are these Q0, which represents the output from the system, and the independent variable is time. So the left hand side of this ordinary differential equation represents how the output changes with time. And if you look at the right hand side, Qn is the input to the system. So this is the forcing function. If I say how my second order instrument will behave if I give a step response, in that case Qin will represent a step input function. Similarly, ramp, sinusoidal function, etc. So the right hand side represents the forcing function. Now, if you look at here, a first order systems will be represented by the first order differential equation, so retain only the first order term. Similarly, a second order instrument, the output of the second order instrument will be represented by second order linear differential equations. So I retain only the second order terms. So second order terms will be here. What will be that? A2 d2y dt square. So this one. And in this case, this is basically nothing but this forcing function Q input. Again, I repeat, let's say for step input, it will be the step function. Xt will be the step function. So this general second order differential equation with constant coefficients can represent the output of a second order instrument or second order system. Now, see why typically we solve this equation by making these coefficient unity. So divide this equation throughout by A0. So this is A2 by A0, A1 by A0, Y, B0 by A0. So now you will see, if you open any process control book or the process dynamics book, you will see that this A2 by A0 is basically, okay, before that, so this equation, if you divide this equation throughout by A2 by A0 both sides, this will be written in the form like this. tau square d2y dt2 plus 2 zeta tau dy dt plus y k into xt. So this equation you're also familiar with from the process control class as a second order differential equation for second order systems. Now this tau square is basically corresponds to this A2 by A0 tau. A2 by A0 tau. 2 zeta tau corresponds to this A1 by A0 tau. And B0 by A0 term corresponds to this K. So this K is called the gain of the process. Tau square A2 by A0 and 2 zeta tau this A1 by A0. This zeta is known as damping coefficient. Note that there are in the first order system you will have time constant tau and gain K as two parameters for the process. Note that if input and output are expressed in the same dimension, same units, this K will basically be unity. In case of second order system, you will have tau, zeta, and K. Now, this zeta is known as damping factor. You are familiar that this is the familiar Laplace transformation. This is how the, if you take Laplace transformation, it will look like. So if you take Laplace transformation of this equation, it will look like this. So now, if I want to find out what will be the output of this second order system or response of this second order instrument for a step input, this XS will be replaced by the Laplace transformation of step input function. So unit step input is this function, and you know the Laplace transformation of this unit step input is 1 by s. If I say Laplace step input, if I say step input of magnitude, not unity, but let's say magnitude 10, you put 10 here. Right. So this, what we have seen in the previous slide as Laplace transformation of these second order systems. Okay. Put xs equal to 1 by s here. And then ys can be written like this. Now, you take inverse Laplace transformation, so you'll get output in the time domain. And this is what you get. Now, the solution, which is these outputs, depends on the numerical value of this damping factor or damping coefficient zeta. Note that zeta can have three different types of values. Zeta may be equal to 1, zeta may be greater than 1, and zeta is less than 1. What about zeta equal to 0? So zeta equal to 0 means there is no damping. So zeta greater than 1, you will have this equation. Please go through this equation carefully. These are all there in the course slides. When zeta equal to 1, you have this form of the equation, and when zeta is less than 1, you will have this equation. When zeta is greater than 1, we call this overdamped response. So this is the example of overdamped response. When zeta equal to 1, we call it critically damped. And when zeta less than 1, you have this oscillatory underdamped response. So many second order systems are characterized by such underdamped response. So their zeta value is less than 1. So you'll get an oscillatory output or oscillatory response from a second order instrument when the damping coefficient zeta is less than 1. You will get an underdamped response. But overdamped response, there is no oscillations. But you look at, for the overdamped response, it takes very, very long time to reach the final output. But underdamped response quickly reaches the final output, but then start oscillating around it. So this figure gives you an idea about how this oscillation decays with increase in damping ratio or the zeta value, damping coefficient. So A, B, C, A is zeta equal to 0. There is no damping. So it will, it will continue to oscillate like this. And damping means the oscillation will be restrained with time. So B, your damping is 0.2. C is 0.707. And when D comes, you have 1. So this is critically damped. Up to this under damped. This is critically damped. And this is higher, greater than 1. So this is over damped. So how will you use this information? So we do not have much time left, but let us quickly look at this. We have discussed this second order instrument. We have discussed this dynamic equation that represents the behavior of the manometer. So you write this force balance equation. Is basically sum of the force P equal to MF relation, sum of the force equal to mass into acceleration. If you do this, identify all the forces that are acting here. Look at this plane C here. These two limbs of the manometers are connected to two different pressure sources, P1 and P2. You have seen the oscillation that takes place, right? And slowly it settles. Now, if you write down the mass balance equation, if you write down the force balance equations, you will be considering the forces due to pressure P1 and P2. Then the force due to liquid level difference and force due to fluid friction. All this will be equal to mass of this liquid, that means mass of this mercury in the column multiplied by acceleration. So after identifying all the terms, please go through the slide, the lecture slide. You will have this equation. Now, this equation reduces to this. And now we can write this equation in the form like A2 by A0 d2 by dt square, like that, or tau square s. Okay, let me show you. So you can write this equation. You can write the manometer equation like this. You divide this equation throughout by B0 and you get this form with appropriate tau square, 2 zeta tau, and K. So this is that equation. Now, if you compare, this tau square is L by 2G. This term corresponds to 2 zeta tau, and K corresponds to 1 by 2 rho G. Note that this is the input. H is the output. H is the liquid level. The difference. That is the output of the manometer. So now you have these all the terms tau, zeta, and k. Note that they are all expressed in terms of parameters of the manometers, like the length of the mercury column, the density of the mercury, all the viscosity. So all the parameters of the U-tube manometer, tau, zeta, k, all are expressed in terms of parameters of the manometer. So all these things can be suitably chosen so that you can have appropriate value of zeta or tau or k, etc. So such analysis will be useful for designing a manometer. So we do not have much time left today, so we'll stop here. So I thank you for joining today. Please put questions on the forum. We'll also have quickly, very soon we'll have another round of live session, second live session, and we'll discuss we'll discuss your questions and concerns again on that live session. Also, we'll answer on the forum. There was one question which says that is there any easier way to write exams? But I'm afraid as it stands now, you have to visit an exam center to write the proctored exam. But the centers are chosen, throughout the centers will be there spread over the entire country. So hopefully you will find a center close to your location, current location. If you have any other specific problems, I would request you to please get in touch with the NPTEL administration. With this, once again, I thank you and